Hello everyone, we are happy to join you today in this edition of HashiTalks. I am Andrei, and alongside Elif will bring into attention Packer's capabilities in the context of adopting a mindset towards immutable infrastructure. A few words about myself. I am a senior solution architect with a focus on designing and implementing complex systems at scale. I have more than 20 years in IT. Also, I am a DevOps consultant with extensive experience in system and network administration, automation, and security. I represent Infinity Group, an IT service company offering managed services, application management, support, and IT strategy consulting solutions from the main office in Bucharest, Romania. Elif is a senior DevOps engineer having considerable experience in implementing, administrating, and optimizing everything related to infrastructure. She has consistently contributed to the HashiCorp ecosystem either by delivering talks or by writing about various topics. We are also two of the organizers of Bucharest HashiCorp user group meetup. So today's protagonist is Packer. What to expect from this presentation? We will talk about infrastructure as code, immutable infrastructure, how Packer fits in all of this, golden images, and we will also provide a demonstration by building a virtual machine image and a container image. So what is Packer? Packer is, without a doubt, one of the tools that shouldn't be missing from a DevOps engineer's ammo bag. Its objective is to create identical machine images for multiple platforms, such as KVM, Vagrant, VMware, AWS, Azure, Google Cloud, or even Docker, from a single source configuration. Thus, it drastically shortens the time it takes to deploy new instances. By baking our need configuration into golden images, we also shift our mindset to immutable infrastructure. This in turn brings some major benefits, such as reducing the deployment time and configuration drifts. Packer is a tool, quite unique, that can generate identical images for VMs or containers based on a set of steps one provides. It can do this from a single source configuration, which helps generate images with all applications, libraries, and configurations already baked into the image. We actually need this feature as a prerequisite when starting to build immutable infrastructure. So where is Packer situated compared with just a few of other popular infrastructure as code tools and in the infrastructure automation landscape? Elif, would you tell us about it?
Sure, Andrei. First of all, thank you for the nice introduction. Hi everyone as well. Let's see how Packer fits it. First of all, let's see, why infrastructure as code? Well, the infrastructure as code approach ensures repeatable deployment. And in order to achieve this, we usually focused on several areas of coverage, as you can see in the image: infrastructure templating, manage the infrastructure, one-time configuration, and post-install configuration and deployments. Thus, speaking about coverage area, Packer is situated in the infrastructure templating level. Andrei, how about Packer history?
Yes, sure. If I was asked to name the top events in the history of infrastructure as code, I would probably stutter at first because of the amount of unstructured information which comes to mind regarding the subject. Thereby, we created this diagram. Packer was first announced in 2013, and in terms of recent IT infrastructure history, it can be regarded as a veteran.
Well, up to this point, we have seen what Packer is and how Packer has evolved. However, what does Packer try to solve? Among some of the use cases, I would mention immutable infrastructure, configuration drift, deployment, and time to market. And nonetheless, maintaining some control over costs. We all know that projects employing good automation generally tend to absorb fewer costs. Let's take these one by one. I have firstly mentioned immutable infrastructure. A traditional immutable server infrastructure dictates that servers are continually updated and modified in place. Well, immutable infrastructure is another infrastructure paradigm in which servers are never modified after they are deployed. Typically, configuration management is only used during image creation. The scope is to make the process of deployment more predictable, other benefits being, for example, consistency and reliability, which in turn translate to a more stable infrastructure. The classic example here is that we switch from doing SSH into the servers to a foreseeable process of replacing the entire server with an image, which upon validation already has the appropriate changes, such as updates, fixes, and configuration changes. Having an immutable infrastructure, this leads to fewer or ideally no configuration drift. Any system configuration will over time diverge from its established known good baseline or even industry standard benchmarks in case you follow these. In reality, even a small drift can expose your organization to data breaches or downtime. Proper configuration and management of infrastructure components is vital to security, compliance, and of course business continuity. Anything from day-to-day operational tasks such as software patching or hardware maintenance, even poor documentation or lack thereof can cause configuration drift. Andrei, you mentioned something about golden images. Do you mind elaborating on those?
Yes, I did mention golden images. As a definition, a golden image is a template for a virtual machine, a virtual desktop, a server, or a hard disk drive. A golden image may also be referred to as a clone image, a master image, or a base image, usually containing up-to-date OS packages. A golden image contains also software and configuration needed for a particular task. Here are some of the reasons to use golden images and the problems they try to solve. One would be image reusability in an infrastructure as code mindset. Also, to satisfy specific configuration or software pre-installed on a given machine, to avoid manually installing and configuring common software, and to save time when deploying many resources at once. Speaking about deployment, we need to tackle with faster time to market. Automation does increase the infrastructure provisioning speed of development, testing, or production environments. Instead of a torrent of manual time-consuming processes, by codifying and documenting every aspect of our systems, we fight slow provisioning and shorten the time needed for scaling or taking down production infrastructure when necessary. In the software development business, a significant aspect of controlling cost is the reduction of operating expenditures by managing time for development, testing, and deployment. Therefore, we have faster time to market by reducing the time it takes to get one's products to market. The ability to reduce the speed to market for new products is the key differentiator identified in high-performance IT shops. Time to market normally includes the time it takes to come up with a product idea, to design and test that cycle, any supplier sourcing and auditing process as well, the deployment to production, and everything else that needs to be done until the product is ready to reach the customer. Now, because the novelty and profitability of any new product rapidly decreases if not launched on time or when copied, it is crucial for margin increase, market growth, and customer loyalty to release your innovative product as soon as possible. Everything we just talked about can be easily distinguished in this diagram by looking at the highlighted area conveniently named profit. This is probably one of the reasons why Gartner predicts that by 2025, 70% of organizations will implement structured automation to deliver flexibility and efficiency, an increase from 20% of organizations in 2021. To talk about managing costs, well, unplanned manual processes can add additional delays which translate to overall costs. Infrastructure as code does capture details about instance types, configurations, security groups, and relationships between all those resources. This is actually an added benefit that helps working with a defined cost policy. Before infrastructure as code, the source of truth for collecting information was the runtime environment itself. By leveraging automation extensively, modern projects employ infrastructure as code to create the opportunity to analyze these complex systems prior to their actual provisioning, thus reviewing everything from the architecture, security, and threat modeling up to cost analysis. The Packer workflow, as you can see, takes a source, which can be a Docker image, an operating system installation media in ISO format, or an existing machine, a clone of an existing virtual machine, etc., and creates a machine on the builder. It can execute tests defined by the provisioners and then will generate some output.
Well, that's a high level of how Packer or the Packer objects, let's say. Thank you, Andrei, for introducing this. Let's break this down and see what templates, builders, and others are. Templates are either HCL or JSON files which define one or more builds by configuring various components of Packer. Packer uses HCL2, HashiCorp configuration language version 2, which includes a number of built-in blocks that one can use. A block is nothing else than a container for configuration. These can be configured in multiple files, and Packer will build the image using solely the files from a directory. Builders are responsible for creating machines and generating images from them for various platforms. For example, there are separate builders for EC2, VMware, Hetzner Cloud, etc. Take for example the vSphere ISO Packer builder, which is able to create new images for use with VMware. The builder takes a source image, runs any provisioning necessary on the image after launching it, then snapshots it into a reusable image. This reusable image can then be used as the foundation of new servers that are launched within the vSphere. For parallel builds, one can create multiple sources, then add those sources to the array in the build log. The sources do not need to be the same time. When that is run, Packer will build multiple images. Provisioners. These are components of Packer that install and configure software within a running machine prior to that machine being turned into a static image. For example, provisioners include shell scripts, Ansible, Puppet. Could be something as simple as installing the latest security updates for the operating system, or more complex managed deployments of an entire application.
Let's talk about post-processors as well. They perform certain tasks after the build has completed. These tasks might be uploading the image to vSphere, generating a Vagrant box files, or importing into AWS. They take the results of a builder or another post-processor and process that to create a new artifact. Those might be tests that upload resulting images to a cloud provider, like we mentioned, even tests that import a container image to Docker locally or can push it to a Docker registry. There are other terms used throughout the Packer documentation where the meaning may or may not be immediately obvious. To mention some, we talked about artifacts, which are the results of a single build and are usually a set of IDs or files which represent a machine image. Worth mentioning here is that a builder produces a single artifact. Builds are single tasks that eventually produce an image for a single platform. We can run multiple builds in parallel. And commands, or basically subcommands for the Packer program, such as init, build, or version, which will perform some job.
Oh, we have seen up to this point what Packer is, how Packer fits into today's DevOps practices, how Packer has evolved along the time, and what are the components that makes Packer the tool it is. Let's see. We are now going to show some examples in which we are going to leverage Packer's capabilities in order to get a KVM virtual machine image and a Docker image. For Camu, KVM virtual machine images can be created using the Camu Packer builder. A virtual machine is made by the builder by starting with the blank virtual machine, booting it, installing an operating system, restarting the machine with the boot media acting as a virtual hard drive, provisioning software within the OS, and then shutting it down. The directory containing the image file required to run the virtual machine on KVM is the output of the Camu builder. Well, while we wait for the build to be finished, what nice stories do you have with Packer, Andrei?
Well, I had an interesting case with Azure which is worth mentioning. You might know that Azure works closely with various endorsed Linux distributions to optimize the images that they published to Azure Marketplace. One aspect of this collaboration is the development of tuned Linux kernels, like they call them, which are basically optimized for the Azure platform and are delivered as fully supported components of a Linux distribution. But from my knowledge, there are no Rocky images endorsed by Azure, so I had to make one. Also verify the ISO's checksum and confirm it hasn't been tampered with. I've used the Camu builder and then converted the result to a supported VHD format. Now, VHD images on Azure must have a virtual size alignment of 1 megabyte. Typically, VHDs created using Hyper-V are aligned correctly, but if the VHD was not created using Hyper-V, it isn't aligned correctly, and Azure will throw an error message when you try to create the image from the actual VHD. Thus, we could use the Camu image command to convert the resulting QCOW format to a VHD format. This is actually what the Packer post-processor can do for us. How about you, Elif? Any Packer stories?
First of all, thank you for sharing this. Your story is quite an interesting use case. And to answer your question in turn, yes, I do have something interesting. Speaking of how we can achieve security using Packer, for a particular project, we had to create virtual machines and to make sure that they pass specific checks against the CSI Docker benchmark. As a very brief introduction to CSI benchmarks, they actually consist of secure configuration guidelines developed for Docker in this case. But you can find others too, focused on Linux distributions or even Kubernetes. Many people tend to think that using cloud services is enough for security and call it a day. While this is partially true, it's actually critical to understand the shared responsibility model and which security tasks are handled by the cloud provider and which are handled by you, or us in our case. Taking virtual instances as an example, cloud providers will take care of the underlying infrastructure, where users should take care of the security of the operating system level. That being said, we are already using Packer to build our golden images, so we found this nice project called Docker Bench Security, and we bundled it with Packer. The Docker Bench for Security is basically a script that checks for dozens of common best practices around deploying Docker containers in production. We used a shell provisioner to run the script with the options we wanted and acted upon the result. Simple, clean, and powerful.
Thanks for sharing as well. I think I have it locally. Let me see. Yes, I do.
Oh, that's
Here it
actually
is.
awesome.
Let's run it. It asks for root. Okay, lots of reds on my machine. Doesn't look that good. Nice.
Well, despite being so red, I think it's a nice example of showing us how to use CSI benchmarks in order to secure our golden images.
Yes. How is the build going?
Well, I think we still have a bit to wait for it.
Okay.
Well guys, actually the image that is currently being built is configured using the Ansible Packer provisioner, which is responsible for running Ansible playbooks. It dynamically creates an Ansible inventory file configured to use SSH, runs an SSH server, executes Ansible playbook, and marshals Ansible plays through the SSH server to the machine being provisioned by Packer. As you already know, Ansible is an open source tool that automates provisioning, configuration management, application deployment, and many other manual processes. One key benefit that Ansible provides is that its modules are idempotent. This means that the result of performing the action once is exactly the same as the result of performing it repeatedly without any intervening actions. In our case, Ansible will execute the common role which we have developed in-house in order to ensure that the servers we manage have a universal baseline. Thus, we aim to achieve some of the following. For example, set certain network configurations such as disabling IPv6, enforce certain SE Linux policy, also ensure that certain packages are installed by default, and ensure that all packages are up to date. Well, this also touches the necessity of maintaining a good patch level. Well, how is the build going, Andrei? Do we still have?
I think it's almost finished.
Almost finished, almost there. Well, we have a post-processor in place, which will copy the resulting image to /var libvirt images. And I think we are going to also use a virtual machine manager in order to test the output. However, I think Ansible is taking a bit some time in order to do its job and do its magic.
Ansible is quite fast actually. I think it spent more time on actually going to the kickstart. Let's see.
Well, guys, as you can see on the screen, the Ansible is at the step of upgrading all packages. Well, a tiny bit of detail. The Ansible role is developed with a certain flag. It's nothing more than a boolean, which allows us to either opt for upgrading all the packages, I was talking before about having a good patch level, or not use it. It actually depends on on our necessity.
I think we can see that here. We're passing upgrade all packages, boolean to yes, or Ansible with extra vars, and also the post processor. Let's see. Still upgrading packages.
Well, I think the upgrade takes a bit of time.
Yeah, it does. Maybe do this more often with some kind of CI/CD pipeline and get an image which is actually more up to date.
Well, this might be a good idea, and however, I think that for the demonstration purposes, it's quite a nice use case, because as DevOps engineers, we always need to ensure that the servers we manage, are always up to date and have a certain security level. Well, I think this might take a bit of time. How about building the Docker image in parallel, Andrei? I think we also have something for that while we are waiting for...
Yes, let's start that as well. This will be fast.
Well, this is indeed quite fast. In parallel, what we have, guys, is a Docker Packer builder, which is currently creating a Docker image. A container is started by the builder, provisioners are run inside of it, and the container is exported for reuse, or the image is committed. What is interesting is the fact that without actually using Docker files, Packer is able to create Docker containers. It is able to provision containers with portable scripts or configuration management systems that are not at all connected to Docker by avoiding the use of Docker files. Additionally, it has a straightforward mental model. Setting up containers is very similar to setting up a regular virtualized dedicated server. The Docker builder must run on a machine that has Docker engine installed. Consequently, the builder only functions on devices that are compatible with Docker and does not support running on a Docker host. Well, Packer does support several builders, and changing the target is just a matter of changing the builder, or using multiple builders in the same Packer file. The build steps are kept intact and will be the same as you build a Docker image or an AWS AMI, for example, or even both at the same time. Well, I think the container is quite ready. What about the other one, Andrei?
Still going.
Oh, it takes indeed quite some time. Well, I do hope that our demonstration or our talk did meet the expectations. Unfortunately, the Packer build for a KVM virtual machine takes a bit of time. However, let's take a quick review of what we have touched in this talk. We have touched topics like quick infrastructure deployment, multi-provider portability, better stability, increased security, and nonetheless improved control over costs. Well, accepting the fact that one of the builds is taking a bit more than we had previously anticipated, we did succeed in building a Docker image using Packer, and what's quite interesting is that voila! That being said, guys, thank you for having us at HashiTalks. We hope that you have enjoyed this talk, and in case of any questions, we are here and will take them gladly. Thank you.
Thank you.